Okay, so today we'll continue with our beginning of chapter 2, where we looked at Ohm's law and calculations of voltage, current, and resistances and power. Today we're going to look at the other two important laws, which is KCL and KVL as pertains to voltage and current. So let's bring up. So we stopped here, right? Series and parallel connections. And one of the things that is very crucial to understanding of a circuit is to quickly observe a circuit and determine which components are in series and parallel. Okay. So again, if you are clear on the fundamentals and we implement those fundamentals in problem solving, every student should be adept at recognizing components in series and parallel. There was one case I wanted to talk about was if you have a series connection, right? If you have a series connection and we have a component E that is connected between C and D, right? So I stated that if you have a third connection, a third or more connection where there was previously a series connection, then the series connection is broken and those components are no longer in series. So there is an exception to that. Okay, and that exception would be if the other end of that terminal, the other end of that component is not connecting to anything, it's left open and unconnected, then the circuit behaves as if it's not even present. Okay. So again, if a component is connected anywhere in a circuit by one terminal and the other terminal is left open and unconnected to anything, then that component may as well not be part of the circuit at all. So as a visual illustration, let's say I have a voltage source, connect a resistor, and then I have another resistor. We'd say that those two resistors are in series, right? Because they only have one connection right there. So resistors are in series. And at the same connection, if I now connect a third resistor, by its first definition, we would say that they are no longer in series. But if R3 is not connected to anything at the other end, there is no path for the current to go through R3. Okay, there is no pathway for current to flow through R3. All of the current that comes from the source will go through R1. Nothing will go through R3. Everything will go through R2. Remember, current needs a closed loop, a closed pathway to flow through. So if there's no closed pathway, if there's an open loop, current's not going to flow through, no voltage drop across the resistor, that resistor R3 may as well not be connected. Hence, R1 and R2 will be in series. Okay. The reason I'm emphasizing this and I'm pointing this out is because later on in this course, and even in other classes, other circuits, you will come across circuits where you will make modifications. Okay. When you make modifications, the circuit configuration, the circuit schematic will change. And when circuit schematic changes, the connections would change. Connections that were previously in parallel may no longer be in parallel. Connections that were in series may no longer be in series, and vice versa. So it would be your job as an engineer to quickly analyze and understand how the circuit is changing and how the components are now connected. Okay. So if it's not connected, R3 is not part of the circuit. And R1 and R2 are in series. Okay, is that clear to everyone? Make sense? One other thing, if a resistor is connected open like this at the other end, what is the voltage drop across R3? 0, right? There's no current flowing through, there's no voltage drop. That means both ends of R3 are the exact same potential. If the difference between these two, between the two terminals of R3 is 0, that means both ends of R3 are the exact same potential. And so here's the second conclusion. If this node, let me mark this as node A and mark this as B. If VA is equal to 5 volts, and let's call this terminal C. If VA is 5 volts, then VC will also be equal to 5 volts. Okay. VA will be equal to VC, or actually the other way around. VC would be equal to VA. So if you have a circuit where you have a resistor that is dangling in the air, it's not connected, one terminal open, no current can flow through, voltage drop across the resistor is 0. If the voltage drop is 0, that means both terminals of the resistor are at the exact same potential. So the connected end could be at 100 volts, then the unconnected end or the open end is also at 100 volts. Right? That's a fundamental EE principle that you'll need to keep in mind. Okay. All right. Let's go to KCL and KVL. How do you say this name? Kirchhoff and Kirchhoff. So I'm from India. When I learned this about 30, 35 years ago, we referred to this name as Kirchhoff. And when I was freshly, I was a grad student. I was in a meeting and somebody was talking about Kirchhoff, and I was like, talking about Star Trek? What? I had no idea what they meant. And then after the meeting was over, I just managed the courage to ask somebody, like, what were they discussing? I felt so dumb. I had no idea what they're talking. And they said, Kirchhoff, KCL and KVL. I was like, what? So, there's a German researcher. The actual pronunciation in German is Kirchhoff. I don't know if that was how they pronounced their name. But if you ever hear me say Kirchhoff, that's who I'm referring to. So Kirchhoff or Kirchhoff is referring to the two laws that he proposed. One was pertaining to current, the other one was pertaining to voltage. Came to be known as KCL and KVL. They are based on the law of conservation of energy. And these are the two fundamental principles in addition to Ohm's law, which we will use to solve for all electric circuits. Okay. These three are the only ones that we need. Ohm's law, KVL, and KCL. That's it. The entire class, the entire principle about EE, electrical engineering, circuit analysis, is based on these three laws. There's nothing else we need to know. Okay. All other techniques, all other principles, all other theorems, they are all derived from these three. Ohm's law, KVL, KCL. So anytime you're performing circuit analysis, you're training to be an electrical engineer, these three are the ones that you need to become intimately acquainted with, very familiar with these three principles, okay? So this is KCL, this is KVL, and you have Ohm's law. Ohm's law plus KCL plus KVL is all we need to be an electrical engineer. Everything else is derived from these, okay? Law of conservation of energy, meaning if you have a circuit with, let's say, multiple sources and multiple passive components that are receiving the energy, the sources are the ones supplying the energy, the components are the ones that are receiving energy. So all of the sources put together will comprise the total energy that is present in the circuit. And all of the energy that is being supplied by the source must add up to the total energy that is received by all the components. So based on those, this principle states that if you have a node or a junction in a circuit, the algebraic sum of all the currents that are entering and leaving that node will always sum up to zero. Okay, it'll always sum up to zero. Voltage law states that you can pick any electrical loop with multiple components. If you algebraically sum up the voltages in that electrical loop, they will always sum up to zero. Okay, so let's look at the mathematical equations we can write based on these. I'm assuming you have encountered work with KVL, KCL in physics classes. Yes? No? Okay. So if you have a preferred method for applying KVL that you are used to and you're comfortable with, then you do not have to follow what I use. Okay, I'm not here to change what you've already learned. If you already learned something and it works for you, great, run with it. You don't need to change that. But as part of this class, I do have to cover this. I'm going to cover this. A KCL basically applies at any node because current is flowing through. KVL applies around any closed pathway or any closed loop in a circuit. So this is I think I had one more. Oh, there it is. All right. All right, KCL, again, sum of all the currents entering and leaving the node should sum up to zero. So simply stated, if you have a node like this, IA, IB, IC, and ID. Typically what I do is, if I want to write an equation, I will put an equal to sign and I will take all the currents that are entering a node, I'll put it on the left-hand side of the equation. Entering and exiting or leaving. This is the simplest and the most elegant way I've found to write a KCL equation. Okay. So in this particular example above, you can write IA is entering, IB is entering, IC is entering, is equal to ID. And that's it, as straightforward as that. Okay. All currents entering must equal all currents leaving. Yep. So IA plus IB plus IC is equal to ID. So based on that, let's look at the example here. Okay. We are given IA 6 amps. IC is given as -2 amps. IB is, let's put down IE also. So IB, ID, and IE need to be determined. Okay. So you have IA and IC given to us. We need to determine IB, ID, and IE. Right. Simplistic example, straightforward. So let's start with IA and IE. If you take the bottom node right there, I have IA going up or leaving the node. I have IE also leaving the node, right? That, of course, cannot be possible. We cannot have IA and IE both leaving the node. So if both are leaving the node, I would sum up and put them equal to zero. Doesn't matter if they're both entering or both leaving, right? Direction is just a formality. That's what we use. We might make an assumption or maybe given to us. But if both of them are leaving, then they both belong on the same side of the equation. So IA is equal to IE, or I can write IE is equal to minus IA, which would be equal to minus 6 amps. Right? They are flowing in the opposite direction, but KCL still applies. The sum of all the currents must equal 0. So we have all currents leaving the node. There's no current entering the node as the direction is given to us. So no currents entering, meaning it's equal to 0. Both currents leaving, so IA plus IE equals 0. And same thing occurs at the exact corner, at the exact opposite corner. We have IC and ID. So I can write, and I'm going to move this here. IC plus ID is equal to 0. Therefore, ID is equal to minus IC. And IC itself is given as minus 2 amps. So minus of minus 2. Hence, ID is 2 amps. Which makes sense. They're both flowing in the same direction. Series circuit, so it has to flow in the same direction. Cannot go anywhere else. And now, apply KCL at either the top node or the bottom node. Calculate and tell me what is the value for IB. If you apply KCL at the top, yes. 4 amps. Anyone else? Okay. So let's see. We apply KCL at the top node right here in the middle. I have IA entering, IC entering, and I have IB leaving. The reason I'm taking it step by step is just because when we get to the other analysis techniques, we'll need to apply KCL at many multiple nodes. So you always want to develop the habit of writing out the variables first and then entering the values. Okay, otherwise you're going to end up making errors in your analysis. So I have 2 currents entering, IA and IC, and 1 current leaving, IB. IA is given as 6. IC is minus 2 is equal to IB. And then IB turns out to be 4 amps. Right? So far, so good. Okay. Then there's a slide on the last page with some practice examples. So I'm going to assign this for student practice. Shouldn't take long for you to get done. All right, KVL. KVL is not as straightforward as KCL. Okay. For KVL, first, you need to identify the closed loop. So closed loop are easy enough to identify. That's loop 1, that's loop 2. You can also have loop 3, which is the outer loop. Okay. Loops can contain other loops inside themselves. Okay. So loop 3 is the outer loop that contains both loop 1 and loop 2. Okay. But KVL applies regardless. Okay. The sum of all the voltages around the electrical loop is equal to 0. With the current, it's easy or it's straightforward to assign a sign or a polarity to the value. So current is entering, put on the left-hand side of the equation. If it's leaving, I put on the right-hand side of the equation, and I have applied my KCL correctly. With a loop, it's not as straightforward. So the way I do it is, I identify the loop that I want to apply for KVL. So let's say I'm applying it for loop 1. For loop 1, I have 3 voltages, VA, VB, and VC. And these should all sum up to 0. Okay, these should all sum up to 0. So I'm going to go around the loop, starting from one point, go around the loop and arrive at that same point. So closed pathway, meaning if I start at the bottom left corner, which is usually my preference, and I start adding the voltages, go around it in a clockwise manner, I end up with 3 voltages, VA, VB, and VC. Okay, so I always start at the bottom left corner and I always go clockwise. It doesn't matter where you start, doesn't matter how you go. Whether you go clockwise or counterclockwise, you will always arrive at the exact same equation. Okay, it doesn't really matter. So if I start at the bottom left corner and I go clockwise, what I do is each of these voltages has a polarity. VA, VB, and VC, they all have polarity. So as I go around the corner, whichever polarity I encounter first, whichever sign I encounter first, minus, plus, and plus, is what I'm going to enter into my KVL equation. So I enter minus VA plus VB plus VC equals 0. The other way of looking at it is also, if it's a voltage rise, you make it positive. If it's a voltage drop, you make it a negative. Does everybody see what I'm saying? If you're going from minus to plus, as you're going along your journey, if there's a voltage rise, meaning you're going from minus to plus, you add it as a positive. If it's a voltage drop, meaning going from plus to minus, you enter negative. Regardless, you will arrive at the exact same equation. So plus VA minus VB minus VC is equal to 0. It doesn't matter at all what you choose. So as I said, some students would already be familiar and comfortable with applying KVL. I'm not here to change that. As long as you're comfortable and it works for you, you can do it quickly and efficiently and correctly. Stick with what you know. If I apply loop 3, apply loop 3 both clockwise and counterclockwise in opposite directions. If I start at the bottom left corner, I have VA, VB, VD, and VE, and they should sum up to 0. VA would be minus, VB is plus, VD is minus, and VE is plus. Again, I'm starting from the bottom left corner and I'm applying in a clockwise direction. Did that make sense to everyone? Okay. Any questions before we go to the example? All right, let's go ahead and find the answers in the time we have left. VA is 10 volts, VC is 15 volts, VE is 20 volts. So find VB, VF, and VD. If you look at the polarities, what do we need? We need, so if you take a loop, loop 1, L1, L2, and if well, let's call this L3. I'm going to call this loop 4. Okay. I can find F directly because I have A, I have E, and I have C. But the easier way to do it is finding B and then finding D. So if I apply KVL to loop 1, I can write VA plus VB minus VE is equal to 0. VA is 10 volts. VB is undetermined, and VE is 20. Therefore, I can write VB is equal to 10 volts. Right, minus 10, take it on the other side, plus 10. For loop 2, I can write minus VB minus VC minus VD is equal to 0. Therefore, VD is equal to minus VB minus VC. Therefore, VD is equal to minus 10 and minus VC, which is 15. For VD is equal to minus 25 volts. And because VD and VF are in parallel but opposite polarity, I can write a KVL expression for L3 loop 3 as VD plus VF is equal to 0. Therefore, VF is minus VD. Therefore, VF is equal to 25 volts. Opposite polarity. All right, it's exactly 4 o'clock. So I'm going to stop right here. We'll pick up here on Wednesday. Recorded lectures will be posted online within the next hour. So we had to go a little bit faster here. But if you have any questions or concerns, please reach out via email. Stop by my office. I'll be in there. Okay. All right. I'll see you all on Wednesday.